Assalamualaikum warahmatullahi wabarakatuh. My name is Rabita Adawabiti Subaan. Today I want to make an explanation about my individual project. So this project is about quasi one-dimensional nozzle flow. This project is about consider the isentropic flow through a convergent divergent nozzle flow. The nozzle shape A equal to AX is specified and held fixed, independent of time. For this case, choose a parabolic area distribution given by A equal to 1 plus 2.2 x minus 1.5 squared, where the interval of x 0 to 3. For S at standard conditions, specific heat ratio gamma is equal to 1.4. Then assume the linear variations of the flow field variables as a function of x. Thus, the initial conditions for this case are given by rho equal to 1 minus 0.3146x and t equal to 1 minus 0.2314x and v equal to 0.1 plus 1.09x t to the power of half, where at t equal to 0. So for question A, the question is by using suitable fluid flow model as well as control volume, sketch nozzle as well as the control volume, derive the suitable governing equation for unsteady quasi one-dimensional flow through a convergent divergent nozzle. Okay, so this is my schematic for convergence divergent isentropic nozzle flow, and then this one is a control volume. Okay, so at here we divide to two sections where this is divergent and this one is convergent. Okay, next we will go through the derivation of governing equation for unsteady quasi one-dimensional flow through a convergent divergent nozzle. So the first one is continuity equation for mass conservation. Okay, so for a finite control volume, the integral form of the continuity equation is this. Then apply this equation to the shaded control volume. This control volume is a slice of nozzle flow where the infinite simultaneous of the slice is dx. So from 1, LHS left hand side is about volume integral. Then from 2, which is right hand side surface integral, is here. Okay, in the limit as dx becomes very small, terms involving differential products go to 0 much faster than those involving only one differential. So substitute into the integral form we have okay, then divide by dx, and noting that d over delta x PAV is in limit as dx as goes to 0. Then the definition of partial derivative with respect to x, where the continuity equations becomes this. Okay, next is momentum equations. The integral form of the x component of the momentum equation for an inviscid flow with no body forces, where the term rho dsx denotes the x component of the vector rho ds. Then we need to apply the equation to the shaded control volume. From left hand side, we cancelling like terms and ignoring products of differentials, the equation becomes in the limit dx becoming very small, like this. Then from right hand side, we cancelling like terms and ignoring products of differentials, the equation becomes in the limit dx becoming also very small, like this. Then we will combine all the equations. Then we get this after divide by dx. Okay, then we subtract equation 7 and 7 minus 8. We will get the equation number 10, which is rho delta u over delta t plus u rho delta u over delta x equal to negative delta rho over dx. And then this is the energy equation. Rho c v delta t over delta t small plus rho v cv delta t over delta x equal to negative rho rt in bracket delta v over delta x plus v delta ln a plus a over delta x. Okay, next question B. By using appropriate non-dimensional variables, list non-dimensional variables. Derive the non-dimensional governing equation for the nozzle which is given. So the list non-dimensional variables is first is this temperature, and this is for density, and this one is for length, dimensionless length, and this is speed of sound in the reservoir. This one is dimensionless velocity, and this is dimensionless time, and this one is dimensionless area. Okay, so first is continuity equation. From continuity, first we need to substitute non-dimensional variables, which is equation 12 into equation 4. Then we need to factorize constant terms. Okay, then divide by extrophies. Then the continuity, we will get the continuity equations here. Okay, next is momentum equation. From momentum, we also substitute equation 12 into equation 10, which is rho delta u over delta t plus u rho delta u over delta x equal to negative d rho over delta rho over delta x. So from equation 10, eliminated pressure by P equal to rho RT. Then we will get the momentum equation here. Okay, last for question B is energy equation. So from energy, we need substitute equation 12 into equation 11. And we will get this. Then note that ratio for a specific heat, gamma equal to Cp over Cv, which is Cp is specific heat for constant pressure and Cv is specific heat for constant volume. Ideal gas law expressed as Cp minus Cv equal to R. R is means gas constant. Okay, so we will get the energy equation here. Is question C. So question C is about the above equations can be solved by using McCormack's technique. Then we need to write the finite difference form, which is numerical algorithm of the governing equation using McCormack's explicit technique. McCormack techniques is they have 5 steps, which is step 1 is predictor step, which is replace special derivative with forward difference. Then step 2, calculate the predicted value at next time label. Then step 3, corrector step, which is replace special derivative with backward difference. Then step 4, average time derivative, that we need to take the average between predictor and corrector step. And the last step is corrected values. Okay, this one is the non-dimensional equation for continuity equation. This is non-dimensional equation for momentum equation. This is the non-dimensional equation for energy. Okay, then this is the predicted value at next time label. Okay, after do all the steps, we finished the McCormack techniques. Okay, next is for question D. Plot the nozzle shape for the given parabolic area A equal to AX using MATLAB. The nozzle shape as a function of non-dimensional distance along nozzle. This is the graph what I get from the MATLAB coding. Okay, then for question E, tabulate the initial condition for the nozzle at T equal to 0 in a table. Hence, by using the initial condition, calculate the flow field variables at x equal to 1 and x equal to 1.5 using uppercase delta x equal to 0.1 and delta t equal to 0.02 in calculations. So this is the table that I got from the MATLAB code. Question F is tabulate the flow field variables rho, T, V, and A across the nozzle after the first time step. Use MATLAB for the calculations. And then from the table that we got from flow field variables after the first time step, this is the graph from that table. The first graph is density, second graph is temperature, and the third graph is about velocity. Question G, let the maximum time step be equal to 3000. To using the subplot command, plot the time-wise variations of rho t P and Mach number at the nozzle throat x equal to 1.5 and at the nozzle exit x equal to 3.0. So this is the graph that I got. This is for density, temperature, pressure, and Mach number. Next question hash. Plot the non-dimensional mass flow rho VA as a function of non-dimensional distance through the nozzle for 0 delta T, 100, 150, 200, 250, 300, 500, 700, 900, 1200, and 3000. Note that the analytic results of the mass flow is rho VA, which is equal to constant, which is 0.579. And here is the graph for nine-dimensional mass flow versus X at different time steps. Okay, question I. Tabulate the flow field variables after 3000 time steps. Okay, question I. Tabulate the flow field variables after 3000 time steps. Okay, this is the table for 3000 time steps. Okay, the last question is, given that P equal to rho T and M equal to V over square root T, compare the value of rho T, P and Mach number M at the nozzle throat when delta X equal to 0.1, which is 31 points, and delta X 0.05, which is 61 points. Discuss the results in terms of grid independence. The exact analytical solutions of the variables are rho equal to 0.634, T equal to 0.833, P equal to 0.528, and M equal to 1. So this is the grid independence study for throat X equal to 1.5. And here is the graph for density versus X, temperature versus X, pressure versus X, and Mach number versus X. So the blue one is for delta X 0.1 and the red one is for delta X equal to 0.05. Okay, so the last one is I put the appendix, which is appendix is the MATLAB coding. Here is my MATLAB coding. Okay, so I think that's all from me. Thank you.